Find the domain of each rational function. First off, let's discuss what a rational function is. A rational function is when you have a fraction. You have x stuff over x stuff. Rational. Rational meaning ratio, root word. So you've got a fraction. Anytime you have a fraction, a number divided by something, that number on bottom cannot be 0. That's how you determine, and we've done this before, that's how you determine the domain. The domain is what values could we put in for x? What values could we plug into this? And the way that you determine what your domain is going to be is the bottom cannot equal 0. So we've got to find out what value would make the bottom 0, and in this case, that value would be 1. So x can't be 1. The way that we had been writing writing the domain, so the domain could be all values from negative infinity up to 1, but it cannot include 1. Or it could be all the values from 1 up to positive infinity, but again, it cannot include 1. So there's your domain. Either one of those would be fine for me. X can't be 1. You can either tell me tell me what the domain is, you can either tell me what x can be or what x can't be. X can't be 1, so therefore it can be this stuff. Now, what we're going to do with the rest of this chapter is what's going on when you have a function like this, what's going on with it at these excluded values. And I'm going to go ahead and show you a graph. Show you a graph of what this looks like. I've got a graph down here. This is the graph of x minus 3 over x minus 1. It's not your normal polynomial graph that we've been covering. These are not continuous functions. You can't draw them without lifting your pencil. And look at your x value that got excluded. It's right here. Look what's going on there. We know that x cannot be 1. Now, x could be things really close to 1. X could be 0.99. X could be 0.999. But it can't be 1, because if you plug in 1, you got a 0 on the bottom. So you have what's called an asymptote line there. And like I said, x can get really, really, really close to 1, but it'll never hit that 1. And that's what an asymptote line is. Your graph, as it approaches an asymptote line, it's going to get closer and closer and closer, but it's never going to actually cross or touch that asymptote line. So that's the first thing we're going to find is we're going to start looking for asymptote lines. And I'm going to teach you how you can look at a function and tell, is there going to be an asymptote line there? Here we go. Next one. Find the domain of each rational function. And again, all you've got to do is the bottom can't equal 0. So we're going to set it equal to 0. We're going to try to figure out what values of x would give me a 0. Move the 4 over, take the square root. X squared equals 4. Take the square root, but don't forget the plus and minus. So x cannot be positive or negative 2. If you want to write it the other way, that would be all the values. X can be all the values from negative infinity to negative 2. Or it can be all the values from negative 2 to positive 2. Or it can be all the values from 2 to positive infinity. There's all the things that x can be. I would rather say this. X can't be those. And again, let's look at the graph, and you'll kind of discover this on your own. What's going on at those values, those excluded values. Here's the graph. And again, look what happens at negative 2 and positive 2. You've got this weird shaped graph, but as you get closer to negative 2, you've got that asymptote line there. This graph will increasingly get closer and closer. Same thing here, it gets closer and closer. Positive 2, you got the same thing going on. Here's the value of positive 2, and you're approaching those asymptote lines as you approach negative 2 and positive 2. So my question is, and this is what you need to start thinking about, so anytime I have an excluded value in my domain, anytime that bottom is equal to 0, do you always just have an asymptote line there? Most of the time, yes, but sometimes, and we're going to talk about those other instances, sometimes no. Sometimes you've got something else going on there. Domains, asymptote lines, and holes. And I've already told you what an asymptote line is. It says a graph can cross. Okay. Okay, I guess I need to turn. here's how you determine what kind of scenario you have. Let's first start out with vertical asymptotes versus holes. Vertical asymptote lines, holes. If you've got the function f of x equals, and I'm gonna factor this thing out just so it looks a little bit better. X plus 3 times x minus 1 over x minus 2 times x minus 4. If you graph this function, I'm not going to, just take my word for it. If you graph this function, you've got two excluded values on bottom here. What are those two excluded values? X cannot equal 2 or 4. Both of those values would be vertical asymptote lines. You could actually plot them on the graph, put them on there, and if you had those two excluded values, your graph would approach them, but they can't cross them. They can't equal that. So that's when you have a vertical asymptote. What about holes? Let's show you the difference between a vertical asymptote and a hole. Which, by the way, what a hole is, I guess that's pretty important information. Let's say that you've got this graph, and all of a sudden it skips. It's nearly like it skips a pixel. Linear graphs can have holes too. And holes are a lot like vertical asymptotes in that x can't be equal to those values. Like this might be an x value of 4 or something like that. But when you have a hole, it's just something that x cannot equal. So by looking at an equation, how can we tell which scenario we have? Here's how. G of x equals x plus 3 times x minus 4 over x minus 4 times x plus 2. Parker, what are my excluded values there? What are the things that x cannot equal? And there's my two excluded values. I will tell you this. One of those excluded values will result in a vertical asymptote, just like over here. The other excluded value will actually result in a hole. Can anybody give me an educated guess as to why one of them might be different? What's different about it? It doesn't. That's a good guess. It doesn't have anything to do with the negatives. See anything else that's different about it? Huh? That's exactly it. Just look at the x minus 4s. You see that you have an x minus 4 on top and you have an x minus 4 on bottom. That could cancel. You could mark those out. But here's the thing. Anytime that something will cancel, anytime that you have something that is a factor of the top and bottom, it's not going to be an asymptote line. It will be a hole. So here you actually have a hole at x equals 4. And you have a vertical asymptote line at x equals -2. That'd be your vertical asymptote line. Now something else that I do want to point out here. It says a graph can cross at a horizontal asymptote. Let's talk about horizontal asymptotes because here we've got vertical asymptotes and holes, but we've not said anything about horizontal asymptotes. Here's what a horizontal asymptote is. We've kind of done a little bit of it in the past. A horizontal asymptote is what does your graph do as it approaches infinity. It might level out and actually get closer and closer to some horizontal value. Okay. And usually to one extreme, if it's doing something to one extreme, it's going to do the exact same thing to the other extreme. That same horizontal asymptote will be present to your as x approaches positive infinity or as x approaches negative infinity. Now here's the rules for this. This is a little bit tougher. It all depends on degrees. Let's see, f of x equals x minus 3 over x squared plus 2x plus 4. Three different scenarios here. G of x equals 3x squared plus 2x plus 1 over 4x squared minus 5. And h of x equals x to the third plus 2x minus 5 over x plus 2. 3 scenarios. Your horizontal asymptote all depends on the degree of your numerator and denominator. In the first scenario, the degree of the top is 1. Y'all remember how to find degree? Degree is the highest power of x. In this case, the degree is 1. In this case, the degree is 2. If the degree of the top is smaller than the degree of the bottom, you will have a horizontal asymptote at y equals 0. Need to know these. The degree of the top is greater. I guess you could put greater and less. If no, I got that backwards. If the degree on top is less than the degree on the bottom, if the bigger one's on bottom, you have y equals 0 as your horizontal asymptote. If the degrees are the same, I put S and S. If the degree on top, in this case, the degree on top is 2, the degree on the bottom is 2. If the degree on top and the bottom are the same, your horizontal asymptote is going to be whatever your what's called leading coefficients are. The numbers in front of your highest powers. Here, my horizontal asymptote will be y equals 3/4. Notice y equals, that's a horizontal line. Your last scenario, if the degree on the top is greater than the degree on the bottom, you will have no horizontal asymptote, but you will have what's called an oblique asymptote. And we'll talk about that in just a second. So again, 3 scenarios while you're writing it down. If the degree of the bottom is bigger, y equals 0 is your horizontal asymptote. If the degree on the top, or excuse me, if the degrees are the same, look at your leading coefficients and just pull those numbers. That's your that's going to be your horizontal asymptote. And if the degree on the top is bigger, then you will have no horizontal asymptote. It will be an oblique asymptote. And that, hopefully now the note there makes sense. It says a graph can cross a horizontal asymptote. It's a different scenario. Like I've seen one graph, might actually be in your homework, where it does something like this. It's approaching, and then it does this wild thing at 0, and then it comes up, and it starts approaching 0 again. So we notice with that graph, you're approaching 0 here. You're getting closer and closer to your y equals 0. Here you're getting closer and closer to y equals 0, but it does this crazy stuff in the middle. Horizontal asymptotes tell you what your graphs do at the extremes, far right and far left. At the far left, this graph approaches 0. At the far right, this graph approaches 0. Okay. So now, here we go. Find all horizontal and vertical asymptotes for each rational function. To find vertical asymptotes, set the bottom equal to 0. X squared minus 1 equals 0. What 2 values, and there are 2, Drake, what 2 values can x not equal there? X cannot equal 1, and x cannot equal -1. And then you ask yourself, are those vertical asymptotes or are those holes? Drake, if I factored this thing out into x plus 1 and x minus 1, will either one of them cancel? These are both vertical asymptotes. Call them VAs. So you have vertical asymptote lines at -1 and you have a vertical asymptote line at +1. Next, let's find horizontal asymptotes. There are no holes. Because look at that, nothing cancels there. Nothing is a factor of the bottom and a factor of top where it would cancel. Now to find your horizontal asymptotes, you simply look at degrees. Michael, what's the degree of the top? What's your highest power of x? 0. Degree of the top is 0, the degree of the bottom is 2. If the degree of the bottom is bigger, you might tell me what my horizontal asymptote is going to be? Y equals 0. So that's all you got to do. With that said, let's look at the graph. You had vertical asymptotes at -1 and +1, which is there and there. And notice again, your graph will never cross a vertical asymptote. It kind of sandwiches your graph. graph. It tells you where your graph's going to be located. Now, what's it going to do in between there? Honestly, you plug in some values to find out what it's going to do in the middle. Horizontal asymptote, y equals 0. There's y equals 0. And again, it sandwiches it. Do you see that? Y equals 0, that's what your graph, as you get bigger and bigger and bigger, your graph approaches 0. As you get smaller, your graph approaches 0. The y value is 0. So there's all your horizontal and vertical asymptotes. Another? Autumn, what's my two excluded values for my domain? So positive and negative 2. And my question is, anybody, will x plus 2 or x minus 2 cancel at the top? No, so these are both going to be x equals, that's going to be your vertical asymptotes. This is very similar to the last one. I don't know why I gave you 2 of these. Your horizontal asymptotes, since the degree of the top is 1, the degree of the bottom is 2, it's going to be y equals 0 again, right? And you see another example of that here. Notice where your vertical asymptotes are at positive and negative 2. And to the extremes, y equals 0, y equals 0. It's approaching that y equals 0 line. But it does do something in the middle, a little bit different there. Okay. The degree of the top and bottom are the same, so your horizontal will be different here. But will anything cancel, first off? Will any of the factors cancel? Can I cancel out x's? No. Please don't. Okay, there are plus signs between them. So I have one excluded value. Austin, what is that one excluded value? So x can't be negative 3 because at negative 3, since it is not a factor of the top, you have a vertical asymptote at negative 3. Since your powers are the same, you have a first power on top, a first power on bottom. Anytime your degrees are the same, you always go to your leading coefficients, which are 2 and 1. Y equals 2 over 1, or just y equals 2 will be your horizontal asymptote. There you see it. You have a vertical asymptote here at negative 3. Your horizontal, you see how it got shifted up? Is there a relationship between this and transformations? Of course. Because what that did, it just shifted that graph up, is what you had going on there. And actually, right there, at y equals 2, you've got a horizontal asymptote in this case. Holes. This one has a hole. X minus 2 over x squared minus 4. Seth, what's my 2 excluded values? X can't be 2 or negative 2. Good. But do you see the issue with the top? If you factored this, and to truly see the holes, you need to factor. You got x minus 2 on top. You have x plus 2 times x minus 2 on bottom. Kaneda, what's a factor there of top and bottom? What's going on top and bottom? Good. No cancel, right? X minus 2's will cancel out, so anybody, which one does that relate to? 2. That is so you have a hole at x equals 2, and you have a vertical asymptote at x equals negative 2. Since the degree of the top is 1, the degree of the bottom is 2, you will have a horizontal asymptote. Anybody, where we're at? Say again. 0. Let's look at the picture. You have a vertical asymptote at negative 2. You have a horizontal asymptote at 0, which is your x-axis. And you have a hole at x equals positive 2. And even this one, it doesn't graph the holes for you real good. If you're graphing one of these by hand, though, let me show you how to graph a hole. You've done it before. Do you know that? At x equals 2, right there you have a hole in your graph. You do an open circle. Think about it when you graph x is greater than 3. How you graph it, do an open circle and shade to the right. It's the same thing. X can't be 2. So on your graph, you would put an open circle at that 2. Okay? Because that's the value that x excludes. Nearly done, guys, I promise. Obliques. Everybody knows what obliques are. Okay. Determine all of the asymptotes, and notice it says all. Not just vertical and horizontal, but all. and I'll show you how to find oblique asymptotes in just a second. Let's start with your horizontal and your vertical. Vertical asymptotes, let's see, what can x not equal? X can't be -2. So the question is it a whole or is it a vertical asymptote? If it is a whole, then x plus 2 would have to be a factor of the top as well. So let's try to factor the top. It'll be good review for us. 2x squared plus 3x minus 5 would be x squared. Using bottoms up factoring, that would be x squared plus 3x minus 10, which factors into x and x, positive 5, -2. Divide them both by 2. You're left with 2x plus 5 and x minus 1. So is x plus 2, will it yield a whole? No. Because x plus 2 is not a factor of the top. That's the top factor, 2x plus 5 and x minus 1. So we've got a vertical asymptote at x equals -2. What kind of horizontal asymptote do we have? Notice the degree of the top is bigger than the degree of the bottom. So what kind of horizontal do you have? None. But since you don't have a horizontal asymptote, more than likely you're going to have what's called an oblique asymptote. Here's how you find oblique asymptotes. More practice with synthetic division. Actually divide that. 2x squared plus 3x minus 5 divided by x plus 2. Use synthetic division, divide it out. Bring down the 2, multiply. Add, multiply, add. Okay, first off, you should not get a remainder of 0. If you got a remainder of 0, guess what? That would have been a whole. Because that would have meant, and with a remainder of 0, that would have meant that x plus 2 was a factor of the top. And you just cleaned it up. You'd have had a whole there. Since you don't have a whole, let's rewrite this thing. So when you divide this, 2x squared plus 3x minus 5 divided by x plus 2 is equal to this, which is 2x minus 1, plus, actually, let's do it as minus because it's a negative, minus 3 over x plus 2. This is pretty cool. I told you that when you're concerned with horizontal asymptotes, and the same thing applies to oblique asymptotes, we're concerned with what happens as the graph goes to infinity, as x gets bigger and bigger and bigger. Now let me show you something. This will get you ready for some calculus. Take something like, this is completely different, but take something like 2 over x. Make x big and bigger and bigger and bigger and bigger. Make x 2, 2 divided by 2 is 1. Make x 4, 2 divided by 4 is a half. Make x 8, 2 divided by 8 is 0.25, a fourth. Make x a 100, make x 1,000, make x 10,000. You have 2 pieces of candy. And you want to divide it amongst 2 people, no problem. Each person gets 1 piece of candy. You want to divide it by 4 people. Each person gets a half piece of candy. You want to divide it amongst 10 trillion people. What happens to that candy? How it happens to the slices of that candy? 2 divided by 10 trillion pretty much is what? 0. Does that make sense? As x gets bigger and bigger and bigger, and you could look at the graph and see the same things happen. If you graph y equals 2 divided by x, and you zoomed out to 10 trillion, 2 divided by 10 trillion, it's pretty much 0.0000, it's pretty much 0. Makes sense. Same thing happens as you approach negative infinity. 2 over x approaches 0. The bigger, or in the opposite direction, the smaller that x gets, that 2 over x goes to 0. And again, you're going to do a ton of that in calculus. Calculus talks about limits and what happens as your x values get bigger and bigger or smaller and smaller. We'll take this now, 3 over x plus 2, and do the exact same thing with it. Approach infinity. Let x get bigger and bigger and bigger. Okay, now we're going to add 2 to it. Does that matter? No. Instead of 10 trillion, we have 10 trillion and 2. It doesn't really matter. That 2 really does nothing. Instead of 3 or 2 pieces of candy, we now have 3 pieces of candy. Does it matter? No, there's 10 trillion people. Okay, it does not matter. So you have 3 pieces of candy to divide amongst 10,002,000,002 people. Pretty much everybody gets 0. It's not going to be enough to even matter. So look at this. We want to know what happens to this as x gets huge. Well, first off, what happens to this as x gets huge? It goes away. And look what you're left with. 2x minus 1. 2x minus 1 is your oblique asymptote. To find an oblique asymptote, use synthetic division. You're going to have a remainder, more than likely. Once you take that remainder, pretty much what you do to find the oblique asymptote, dump your remainder. I want you to know why you dumped it, because that remainder is going to be so insignificant as you approach infinity that you can get rid of it. So my oblique asymptote here is 2x minus 1. Let's look at a graph of this. This is a pretty neat graph. Let's do it without them. So we had let me write down the 2x plus 1. We had a vertical asymptote at -2. You can still see it there. Here it is right here. You had a vertical asymptote at -2, and you have an oblique asymptote at 2x plus 1. Which means as my graph approaches infinity, it actually approaches, as x gets bigger and bigger, as x gets smaller and smaller, we actually approach that. Let me pull up the other one, you can see it a little bit better. Here's the line 2x plus 1 graphed along with that graph. And as you go that way, do you see the blue line gets closer and closer to 2x plus 1? As you go to the left, your blue line gets closer and closer to 2x plus 1. I think we got maybe one more. Nope, maybe not. We don't need summary. Sketching the graph. We're not going to go through these, but let me just explain. To sketch one of these graphs, what I do first is I find my horizontal and vertical asymptotes, which in this case would be -2 and +2. I find my, that's my verticals. I find my horizontal asymptote, which in this case would be y equals 0. And I just keep in mind that my graph, and you're sketching a graph. You're just kind of sketching about what it would look like is all I'm concerned with. I know my graph is somehow sandwiched in between here, and I can cross that that horizontal asymptote. So what would I do now? I'd plug in a few points. Let's say that I plugged in some points and I got something like that. I plugged in these 3 points, so I just follow those asymptote lines, and I know that it'll look kind of like that. I plug in some points in the middle and I get something like this dot, and this dot. Follow the asymptote lines. It's going to come down, it's going to cross, and then it's going to get closer and closer over here. I plug in some points on this side. Let's say I get these 3 dots. So sketch your graph. That's what your graph's going to look like, something to that effect. Find your asymptote lines, plug in some x values to find some points, follow your asymptote lines. It cannot cross a vertical, so you know it's going to be between the verticals. It's going to get closer to it. It's never going to cross it. It can, notice in the middle, it can cross a horizontal. Okay. All depending on what your x values do. That's enough of those. 2 more problems. Rational inequalities. Rational inequalities. My suggestion here is move everything to one side. Have it less than or equal to 0 instead of less than or equal to 2 in this situation. Let's begin by saying x plus 3 over x minus 2. Let's take our 2 that's on the other side, move it over, and write that as -2 is less than or equal to 0. Because then what you're asking, think back to what an inequality does. I want to know where is my graph below, because that's what less than or equal to means, below or equal to the x-axis. Y equals 0. Where's my graph below the x-axis? And if you want to, honestly, you can graph it. You can use your graphing calculator to graph it and look and see to give you an idea. But let's clean it up, and I'll show you how to do it by hand. I need a common denominator. We're going to multiply top and bottom by x minus 2. just to clean it. I now have x plus 3 minus 2x plus 4. Now it's got that common denominator of x minus 2. That'll be negative x plus 7 over x minus 2 is less than or equal to 0. And I need to know where is my graph below 0, where's my graph above 0. And I can share this with you. There's only certain places where your graph can jump from above 0 to below 0. And we talked about it a little bit with polynomial functions. Well, these are zeros. This is where my actual equation is equal to 0. So that's one place it can jump it. But now, since you're dealing with rational equations, there's another place where it can jump from top to bottom. These are not continuous functions. What if you have an asymptote line? From one side of the asymptote line to the other side of the asymptote line, you could jump from above 0 to below 0. So you got to be careful about asymptote lines. That's one place you have to check. What about it at holes? Could it ever jump from top to bottom at a hole? Sure. So what we're going to do, we're going to find all of our zeros. We're going to find all of our holes. And we're going to find all of our vertical asymptotes. And we're going to check and see, is my graph above or below at each of those? Or again, guys, look up there. You've got the graph right here. You could check it like that. I'm going to show you how to do it by hand. The next one we'll do it with a graph, and it's a whole lot easier. Because, again, what if you're standing in the middle of Walmart and somebody asks you to solve one of these inequalities and you don't have a graphing calculator with you? You need to learn how to solve it by hand. So first off, let's check for holes and vertical asymptotes. I have only one. Where's it at? 2. That's a vertical asymptote at 2. We're checking now. I need, there's no holes, but there is a 0. There is an x-intercept, and what's real close, we hadn't done any of this, what's real close on how I find zeros? I need to know, where is this equal to 0? There's only one way a fraction can equal 0, and it makes it so much easier. What is the only way a fraction can be 0? If the top is 0. So pretty much what you're checking is, to find vertical asymptotes, check where the bottom's 0. To find a to find a 0 or an x-intercept, check and see where the top is 0. What is my x-intercept there? Set that equal to 0. Negative what plus 7 is 0? Negative 7, right? So if x is 7, that's my x-intercept. So all you have to do is, I know that we're possibly crossing at 2 and at 7. Here's how I do it. I take numbers in these intervals, like 1. 1's over here somewhere, and plug it in. And I see, is it positive or negative? Because what? When I plug in 1, I get 6 and negative 1. That's a negative number, right? That means my graph's down there. If I plug in 1, I get a negative number. It doesn't matter what number you get a negative number. That means over here, your graph is down here. Now at 2, I need to know, at 2, does it cross or does it stay down there? So what do? Plug in a number in this interval. Let's try 3. We plug in 3, I get 4 over 1. That's positive, right? You see that it crossed there? It was down here, now it's up here. Now let's check a number over here like 8. I get a negative on top, I get a positive on bottom, that's a negative answer. So you see what your graph did. You're not concerned with where what your exact values are, you're just concerned with where is your graph. Because I need to know, where is my graph below the x-axis or negative. And notice that when I plugged in 1, I got something below, so I know my graph is below here, or equal to. That's where it's equal to. Or no, it's not. Lied to you. X cannot be 2, so that'd be an open circle there. And I know that my graph is below or equal to there. So my solution set looks like that, and the graph backs it up. Where is my graph less than or equal to 0. There's the graph. Here it's less than 0. Here it's above 0, which was from here to here. You see that? And then at 7, it crossed and went below 0. So my graph is below 0 from negative infinity up to 2. Not including 2. 2 is a vertical asymptote. Or my graph is below from 7 up to positive infinity. That's what your answer would look like. Graphing calculators are going to make your life a whole lot easier. Because look on this next problem, how much faster this is. I need to know where is that graph above 0 or equal to 0. Well, first step, let's graph it. And I know I can look at it and I can see something's going on at positive and negative 1. Should be. This is the wrong graph, isn't it? So let's go with it. We're good there. So you've got asymptote lines here and here, not zeros, my bad. So you have an asymptote line there, have an asymptote line there. So you could possibly cross there. You have a 0. What's going to be my 0? Negative 3, right? So that's another possibility. You don't have any holes. So where is my graph above 0? It's not here, but it is here. And that value is at negative 3. So from negative 3, since it does include it, or equal to, from negative 3 to, what was that, negative 1? I know that in this interval that we're above it. But from negative 1 to positive 1, see where your graph is at? It's below it. It jumps back at this vertical asymptote. It jumps back from being below to all of a sudden now it's back above. So from that asymptote line, not including it, because again, x can't be equal to that. So from 1 to positive infinity, it's going to be above it still. So where's my graph above or equal to 0? From negative 3 to negative 1, or from 1 to infinity.